Okay, thank you. So first of all, I would like to thank Nastya and Stefano for the invitation. It's a pleasure to be here. So we can see the title of my talk here. And of course, it's good to know that this is a joint work with my PhD student, Anna Dolezhalova, with Honza Mali, and with Nastya. Okay. So let me state what is the problem that we are interested in. So of course, we are talking about some models of nonlinear elasticity. So we have some body in Rn mapping from Rn to Rn. Of course, as usual, we assume that the mapping doesn't change orientation. It's a minimizer of some reasonable energy. And the question that plenty of people are asking, is the minimizer one-to-one? So because of the interpenetration of the matter, two parts of the body cannot be mapped to the same place. So, okay, so what are the natural things used? So what is very often used is an approach of John Dole, which works in W1pp bigger or equal than the dimension. If the energy term contains some terms like some ratio of the derivative and Jacobian to some power, and if you know that your mapping is a homeomorphism on the boundary, so somehow I assume that I'm holding the body on the boundary, it's minimizing energy inside. And I would like to know that it's also sort of one-to-one inside or even homomorphism inside. And for this sort of energy, it really happens. And there are plenty of extensions, but this is sort of crucial there. Then, of course, we have seen in several talks already the Sziarlet-Nečas condition. Again, for P bigger or equal to the dimension, if we have the Sziarlet-Nečas condition, we know that our mapping is one-to-one. Okay, so I would like to go below P bigger than n. So then there is a very useful paper by Miller and Spector where they introduced the inf condition. So here P is allowed to be strictly bigger than n-1. Again, mapping doesn't change sign. And F satisfies the so-called inf condition. I will do a proper definition on the next slide. It means something that what is inside stays inside, what is outside stays outside, okay? Something very natural. Precise differential is coming. And under these rather natural assumptions, you gain that your mapping is really one-to-one almost everywhere, which is what we want. And you have plenty of other natural results, that you have disjoint balls, that the images are essentially disjoint. Perfect. Under some additional assumption, you can show that the distributional Jacobian is equal to the pointwise Jacobian plus some sum of Dirac masses. And each of these Dirac masses corresponds to some created cavities. And this AI positive corresponds to the mass of the created cavity. So this model incorporates cavities. Your mappings could be discontinuous, which is very useful because in some real deformation we see some discontinuities. Okay, and of course what is very important, if you want to do calculus of variations, if you have a sequence of mapping satisfying the inf condition that is weakly converging to some mapping, the limit is also in the same class, because without this you cannot do calculus of variations. Perfect. So, very nice class. Of course, all homomorphisms satisfies the inf condition, because if you have a homomorphism, what is inside stays inside, what is outside stays outside. Perfect class for our consideration. So let me briefly recall what is inf condition. So if we have a Sobolev mapping, we know that on almost all spheres, the restriction is in W1P. So we are in W1P, P is strictly bigger than n-1 dimension of the sphere, which means that the mapping is actually continuous. So this is a continuous image of a sphere, so it's well defined. So if you have this, you really know what is inside and what is outside. Formally, the degree is non-zero, the degree is 0, okay? But I say that the mapping satisfies the inf condition if for any point and almost all radii, what is inside is mapped inside the image of the sphere, and what is outside is mapped outside of the image of the sphere, okay? So this is really nice, and as we have seen on the previous works really well. But of course then, okay, let's say that the most important case is n equals 3. And the most interesting energy is the Dirichlet energy, okay? But unfortunately, so far, we assume that P is strictly bigger than 2. But of course, we would like to have Dirichlet energy. But so far, we cannot. in what I have taught. By the way, there will be a talk by Marco Barchiesi and Carlos Moracol. They have some results in this direction. It will be on Thursday. I'm very much looking into it. It will be also about the inf condition in this limiting case. They take care about axisymmetric mappings. So what can you do in this limiting case? There is a very nice paper of Conte and Dalalis, where they essentially introduce the inf condition also in this case. But you have to keep in mind this is slightly dangerous because your mapping is no longer continuous on the sphere, and the image of the sphere really could have some special form of discontinuities, okay? But still, even with those special form of discontinuities, you can still say what is inside and what is outside. But this is non-trivial, because you cannot use the usual degree, which is only for continuous mapping. But fortunately, there is some degree, some analogy of the degree introduced by Brezis and Nirenberg. You can still say what is inside, what is outside. You can still define the inf condition. And you can still define the class of mappings satisfying the inf condition, and it has a plenty of great properties that you would like to have. So again, if you have this inf mapping where the Jacobian is positive almost everywhere, your mapping is 1-to-1 almost everywhere. Perfect. Images of disjoint balls are essentially disjoint. Perfect. Again, the Jacobian really tells you where the cavities are created, but there is one tiny disadvantage. You can find a sequence of homomorphisms, so they definitely satisfy the inf condition, that converge weakly in W1 and -1, but the limit doesn't satisfy the inf condition. So this class is no longer closed. So somehow forget about direct methods in the calculus of variations. And this is really ugly mapping that you would not like to have in your class of competitors. Okay? So somehow, on the first glance, up to here, it looked that this is a great class for our approach, but this is telling you, well, forget it. And the question is, can you somehow fix it? Can you add some other terms to the energy functionals under which you would know that this cannot happen? And this is what we wanted to achieve, okay? And this is what this talk is about. Here, P is equal n-1. Sorry, P is n-1. Yeah, I'm slightly sloppy in my slides. Thank you. Okay? Okay, so how to fix this unfortunate thing? And here's one thing, add to the energy some 1/Jacobian to some power and everything is fine. Okay, try to use the usual Neuhickian energy. So we are in dimension at least 3, A is some stupid number. We have some domains, we have homomorphisms that are equal to a given homomorphism on the boundary. So we fix the boundary values. We have homomorphisms with positive Jacobian almost everywhere. They are uniformly bounded in W1 and -1, so this is what the energy must contain. And also the energy contains integral of 1/Jacobian to this power. And if these two are uniformly bounded, and if you have the weak limit, then already you are in no trouble anymore. The trouble already is nice and lies in the correct class. And this stupid A is sharp, at least in dimension 3. We did the detailed counterexample in dimension 3, but we believe it works in any dimension as well. So if you are in dimension 3 and A is strictly less than this, then you can find a homomorphism, which is identity on the boundary, Jacobian positive, but again, you know, this energy, the crucial energy, is controlled, but it's converging weakly to something which doesn't satisfy the inf condition. So somehow, if you want to think in the terms of the usual Neuhickian energy, this is the term you need to have there. But of course, you know, in reality, we prove something even slightly better, okay? What we really prove that we assume the integrability of the distortion to some power. So this is much weaker condition. But of course, some people don't work with mappings of finite distortion. And actually, the proof is then really simple because integral, so we have here distortion to power 1/n-1. You use Hölder's inequality. Here you have the integral of 1/Jacobian to some power. Here you have the integral of derivative to power n-1. And you know that this is finite. And if this is finite, that this term is finite. Okay? So actually, sorry, slightly misleading. We are really proving that we assume this condition instead of this condition. And if you have this condition, it is just a simple Hölder's inequality that this term is controlled. But this requirement is much weaker, essentially. And of course, this condition already appeared before in the literature in the paper of Pekka and Honza, where they studied the validity of the Lusin and inverse condition for mapping of finite distortion. So this is not the condition that we have invented, sort of. Okay, so perfect. So we have some nice condition under which we know that the mapping is in the inf class, and we have some condition which prevents it. And then we have a follow-up paper with Nastya, and it claims the following. So again, we have a sequence of homomorphisms that are equal to a given homomorphism on the boundary. Jacobian is positive almost everywhere. They are uniformly bounded in W1 n-1. And instead of integrability of 1 over Jacobian, it is enough to ask this condition. So this adjugate matrix is the n-1 times n-1 subdeterminants, okay? So if you are bounded in W1 n-1, this is definitely uniformly bounded in L1 for free. But we ask something slightly more, that it's sort of equi-integrable, okay? So it's not in L1, but let's say L log L, or L log L, anything, we don't care, something slightly better. Of course, for polyconvex energy functionals, this is not unnatural conditions. And again, if you have something in the limit satisfies the inf condition. So this is a different set of assumptions that allows us to get the right conclusion for the limit mapping. Great, and also we have the moreover part. So if we know that our mapping satisfies the Lusin n condition, so maps the null sets to null sets, and for homomorphism Jacobians, I mean, integrals of Jacobians are uniformly bounded by the measure of the image, but we need to assume that the equi-integrability of the Jacobians. Then under these assumptions, the limit satisfies the n condition as well, which is perfect. We have lowest semicontinuity of polyconvex energy, so the calculus of variation really works, no problem whatsoever. And if the domain isn't stupid too much, then there is even the inverse of our mapping, okay? So we really have the inverse in a sense that F composed with HY equals Y almost everywhere, and what is the other? Fx, H equals X for almost every X. So the mapping is invertible and the inverse is in W11. And your H is W11 weak limit of Fk inverse. Okay. So the most important thing, under some additional reasonable assumption, you have lower semicontinuity. And this moreover part holds also with the previous paper of Jan Malý. Okay, so let me return to the previous result of Jan Malý. So essentially, here, moreover, if your Fk satisfies the Lusin n condition and Jacobians are equi-integrable, then you have lower semicontinuity of the corresponding polyconvex energy functional, and the limit satisfies the n condition and so on. So everything is great, and you can really do calculus of variations. And in the paper, just for fun, we really added a small section telling you, imagine that you have this polyconvex energy functional with the corresponding growth containing the terms. You minimize over the class of weak limits of homomorphism, and the minimizer really exists. So really, calculus of variation is now available even in this class. Perfect. So now I would like, oh, what I forgot to tell you. This talk is divided into two parts, the simple and the difficult one. This is the simple, and the difficult one will be given by my students when she will talk about the proofs, okay? This is what you have PhD students for, okay? Remember. Fine. So I will just tell you a few brief things about the proofs. So now the next slide I would like to spend with the counterexample. So you can imagine how the inf condition can fail in the limit. So this is a 3D example. So everything is rotationally symmetric around this axis. So imagine that this is rotated, okay? So now, what is really happening? So we have some ball of radius 2, which is mapped to this drop-like object, okay? And now I would like to see what is happening on these two spheres. So I have here a sphere of radius 3/2, which is divided into the full part and into the dashed part. The full part is mapped here, and the dashed part is mapped here. So the image of this sphere is some sort of horseshoe, okay? Now you have a ball of radius 1/2, again, full part, dashed part. The full part is mapped here, the dashed part is mapped here. So again, you see some sort of horseshoe. The horseshoes are nested. It's really easy to imagine that the mapping is really nice, homomorphism, whatever. Of course, everything is rotated around the axis, even though it doesn't look so. This is, my handwriting. Sorry for that, okay? And now you pass to the limit. So what is happening in the limit? So in the limit, you have those tips or the horseshoes. They all go to the origin up here. That's one thing that is happening. And in the limit, you see this tiny angle, tiny pi, which is shrinking to 0 in the limit. So in the limit, the tiny pi is not there at all, okay? Which means that the image of this sphere is this and this as before, no problem. But the image of this sphere of radius 1/2 has only the dashed part, okay? Because in the limit, the full part disappeared, okay? And now I would like to convince you that the limit doesn't satisfy the if condition. So why is it? Let us have a look on this ball. So the image of the boundary, the image of the sphere is this dashed part, okay? So obviously from the topological part, the topological inside is this, okay? But if you see where the inside of this was mapped, the inside of this was mapped somewhere here, somehow, on the outer part of the dashed thing. So in the limit, whatever was here is mapped on the outer part here. So not inside, but outside. So, and if you compute the degree, which can be done, so originally the degree was 1 everywhere, now the degree is -1. So we were able really to change the degree from 1 to -1. In the original paper of Conte and Dalalis, on a somehow similar idea, they changed the degree from 0 to 1, okay? We used this construction, which is slightly different because we needed to control not only the integral of the derivative to power n-1, but we needed to control the 1/Jacobian to the stupid power. So we needed some very careful construction, and this was easier for us. Also, I would like to convince that you can do something nasty like that really with the Sobolev energy control. The only troublesome part is this pi. If you imagine there is something really tiny, which is mapped to something really big. So here, there is a big integral of the energy, okay? How big it is. Let us have a look on this pi, which is roughly some two-dimensional ball of radius delta, okay? Some disk, which is mapped to something really big. So let's say it's mapped to two-dimensional ball of radius 1, okay? Then the integral of the derivative is the size of the disk, delta squared. So this is rotated, so delta squared. And the derivative is roughly 1 over delta, if you stretch uniformly, okay? So the integral of the derivative squared is roughly 1, so bounded. Now you have to integrate for radius from 0 to 1, but still you have uniformly bounded energy. So even though there is a lot of energy on this really tiny triangle, the energy is actually bounded. Okay, so there is no problem then. Also, what is sort of worth pointing out, that if you think about it, that now you have a sequence of homomorphism. They have bounded energy in W1, 2, so they converge to something weakly. they converge pointwise to this mapping, so definitely they converge weakly to this mapping, okay? But they cannot converge strongly, because there is very tiny portion where the energy is lost. So the FK have here some energy, they have to, but the limiting mapping doesn't have any. So this particular sequence of homomorphisms is converging weakly but not strongly. So why I'm pointing this out, there are very nice results in the planar case. For P bigger or equal to the dimension, it was first done by Yanni and Tadeusz, and then later it was extended to all cases of P by De Filippis and Aldo, that if you have a class of weak limits of homomorphism and class of strong limit of homomorphism, that they are the same. Whenever you have a mapping which can be constructed as a weak limit of homomorphisms, then there are possibly different sequence of homomorphism which is converging strongly, which is so very useful somehow if you try to do calculus of variations, because naturally you apply direct methods, you have some sequence which is converging weakly, and you know that the potential minimizer is much stronger. It is even a strong limit, okay? So this is really nice that these two classes are the same in the plane. But what we were also able to prove with essentially the same proof, that if we are in dimension 3, we converge strongly in W1 n minus 1, then the limit satisfies the inf condition, okay? Which means that if we take our counterexample from the previous slide, it is a weak limit of homomorphism, but if it was a strong limit of a different sequence of homomorphisms, it would have satisfied the inf condition. It does not, so it cannot be obtained as a strong limit of homomorphism. So especially in dimension 3 for P equals 2, we know that the classes of strong and weak closures of homomorphisms are not the same, okay? We expect the same is true in any dimension for P equals n minus 1, but we did not do it in detail, okay? Because the counterexample was sort of complicated enough. So now, the proof of the positive statement will be done by Anička. It's hard, I don't want to talk about it, okay? Now I would like to say a few words about lowest semi-continuity. I said that we can really do the lower semi-continuity of the energy, so I would like to point few brief points why is it the case. So of course, at the end, we will use the De Giorgi theorem, which we have seen the proof of or something like that, right? Yesterday. So we have some functional, we have variables, and of course the most important is the last one. And in the last one, we assume that we have a weak convergence in L1, then we have lower semi-continuity, and we have, of course, have convex thing in the last variable. So for us, as usual, in polyconvex energy, the last term contains derivative, 2 times 2 subdeterminants, and the usual determinant in dimension 3, okay? So, of course, if we converge in W1 n minus 1, this term is converging weakly, that's for free. And we need also that this is converging weakly to this function, and this is converging weakly to this function, okay? And as soon as we have that, we have lower semi-continuity. Standard. So what is also standard that we have if we have a uniformly bounded thing in W1 n minus 1, and we have equi-integrable adjugate matrices, that this is something that can be found already in old board papers. This is for free. So what is really tough, and that we need to verify, that the sequence of Jacobians, which must converge to something weakly, is actually converging to the Jacobian of the limit. This is the tough thing that needs to be done. And also what I would like to stress, that under our assumptions, we not only know that the mapping satisfies the inf condition, but we know that the measure of the ball is converging to the measure of the ball, in a sense that the symmetric difference is tending to 0 even. And I will try to draw what I have in mind. Let me use some pictures. Topological image of the ball. You know. Thank you. So imagine that your mapping is not satisfying the inf condition, which means that you have the image of the sphere, and you have some set inside which is mapped outside, okay? And of course, your homomorphism, which is close to the original mapping, is sending this sphere to something which is really close to the image of the sphere in most of the places, but in some places it can do something stupid. This is really what is happening in the counterexample. And of course, the red thing is a homomorphism. This is inside, it must stay inside. And we are saying that this is not happening. The if condition holds, which means that really the volume of the red thing is roughly the same as the volume of the white thing. And the symmetric difference, the volume is tending to 0, okay? So this is easy to believe that the if condition is really meaning something geometrical like that, okay? So symmetric difference is tending to 0, and I would like to show that under our assumptions, the Jacobian converging quickly to the Jacobian, okay? So recall the assumptions because everybody forgot. So we have Jacobians that are equi-integrable, so not bounded in L1, but L log L or something like that. And we know that the symmetric difference of the image of the ball and image of the ball tend to 0. So first we assume that our fk satisfy n and that the limit function satisfies n as well. So of course, assume that you have a set of measure 0. You would like to see that the image has 0 measure. You cover the set by balls that have small volume. You know the equi-integrability of the Jacobian, and you know that fk satisfies the nth condition. So if you want to compute this, you can use change of variables. Change of variables for homomorphisms holds if you have the Lucin n condition. And of course, if these functions are equi-integrable, the union of bi is really small, the integral is as small as you wish by the equi-integrability, and this epsilon is the same for any k, sort of, okay? And now you know that measure of the ball by k or by b is the same, which means that since this is small, then this must be also small. And if you do it formally with some technicalities that I try to avoid, you have the Lucin n condition for free, okay? Covered by balls, images by f or fk are roughly the same. Images by fk have to be small because of the equi-integrability. It has to be small. So now, as I told you, I would like to prove that this is converging to this, to have semi-continuity. We know that this sequence is equi-integrability, so it must be converging to some L1 function. We don't know if it's a Jacobian of f at the moment. We know the n condition for fk, so we know this as before. And of course, this is converging to h, so when k tends to infinity, this is converging to this integral, okay? Now, at the same thing, we know that these measures of the balls converge to these measures. Here, we already know that f satisfies the n condition, so we can compute this by the integral of the Jacobian. Since we know some properties of the distributional Jacobian, I mean, something is used here more, but essentially what is the most important? You know the Lucin n condition, so change of variables holds also for f. So, and by these two lines, you know that the integral of h and integral of the Jacobian are the same on all balls. So now you look at Lebesgue points, whatever, and you see that these functions are really the same, okay? So this is just to tell you that really the inf condition is telling you that the measure of the image of the ball is converging to the measure of the image ball, so everything works and then sort of in a standard fashion. Perfect? And now, of course, some open problems, okay? So far I have told you what we know. So what we don't know. So what we have shown that if you have a class of weak limits of homomorphisms, that everything is fine. And it's closed and the inf condition is in the limit. But for the original class of inf, it was true that it's closed under a weak limit by itself. So whenever you have fk's that satisfies inf, they weakly converge to something. that the limit also satisfies the inf. And we don't know it. We know it only for weak limit of homomorphisms. And it could be the true in general. Of course, we can discuss what is better class for your calculus of variations. Is it the inf class, or is it the class of weak limits of homomorphisms? Because you have the result so far only for weak limit of homomorphisms, you can pretend that this is the right class, okay? And that even has some small logic, okay? Because it was shown by Aldo and Guido. Aldo woke up, sorry. That there is a mapping which is in the inf class, but it's not a weak limit of homomorphisms. And that mapping is ugly. And I don't want it in my class of competitors, okay? But if you want to do your calculus variation only in the weak limits of homomorphism, you are fine by now. If you want to do your calculus of variation in the inf class, you would need some result like that. Most of our steps works, but some of them fails miserably. When I was telling this open question to Honza, he asked me that there is even better question. So if you don't know how to solve it, there is even more general question that could be true, and we don't know how to solve it. So it might be true that whenever you have a W1 n-1 mapping, which is a mapping for finite distortion, and the distortion is integrable with the correct power, is it automatically true that it satisfies the inf condition? Might be. And of course, as I have touched, so we believe that in any dimension for p equals n-1, we can prove that the weak and strong closure of homomorphisms are not the same. But unfortunately, it really works only for p equals n-1, because of some isoperimetric inequality, whatever. And we have absolutely no clue what is happening for other values of p, which is sort of surprising. I wouldn't be surprised if it holds up to some p and then it fails or something. But here we know it just for this value of p, and the rest is who knows. Okay? So, and I think that's all I wanted to say. Thank you for attention.